But what I'd like to do is I'd like to give you 2.5 lectures, I guess, and I'd like to structure them in a way that today we're going to be focusing more on supervised learning, and tomorrow we're going to be focusing a bit more on unsupervised learning. So let me first start by saying that we live in the space of large data, right? Big data. You've probably heard this term. If you look at the space of images, language, speech, if you look at social networking data, scientific data, a lot of what machine learning is all about and deep learning is all about is to develop statistical models that can discover interesting structure or interesting relations, constraints from data. And also, how can we build models, robust models that can deal with missing measurements, non-station distributions, and multimodal data. And throughout this tutorial, I'm going to show you some of these examples. Let me just point out the impact of deep learning. It's actually been quite an amazing, and a very exciting development. If you look at the space of speech recognition, computer vision, even in recommender systems, and now even more, we start seeing deep learning applications in language understanding. In places like drug discovery, medical image analysis, it's another area that's exploding right now. But before I get into the details, I just wanted to show you one particular example, one particular use case, trying to understand images. So this is an image of Antonio Torralba. He is a professor at MIT that I took of him, I guess, a couple of years ago at NIPS. And what you can do is you can tag the image, right? You can use deep learning to tag the image, which is a very useful thing to do. So here it tags it as strangers, coworkers, and such. But at the same time, maybe you'd want to develop a system that actually tells you in natural language what this image is about. And one way of doing that would be to find the closest image in your training set and just copy the corresponding description or a caption. So this would be in the nearest neighbor sentence, and that's what it says, people taking pictures of a crazy person. But if you develop the model, sort of the multimodal model that takes an image and actually uses recurrent networks or neural language models to generate sentences, this is what the model does. Right? A group of people in a crowded area, a group of people are walking and talking and such. So these kinds of systems have been working surprisingly well. It was surprising to a lot of folks in the computer vision community as well. And now there are even more advanced systems based on visual question answering and such. So my tutorial today, in today's lecture, we're going to be really focusing on discriminative learning or supervised learning, in particular look at neural networks. And tomorrow's lecture, we're going to look at the unsupervised learning and looking at generative models, and also try to cover some of the open research questions, like what are the key areas that you're seeing a lot of research taking place. Okay. Okay. So let me start by just basically getting the setup. Just to be fairly precise, suppose we have a set of labeled training examples, X and Y. X is the input, Y is a particular target. Let's say it's a class or a regression. And we're going to be performing empirical risk minimization, right? And what do we see here? Well, F here is going to be a nonlinear function mapping inputs to outputs. And we're going to make an assumption that it's parameterized by parameter theta. Typically, because F is a nonlinear function, it will be our multilayer neural network. The entire system, the whole optimization is going to be non-convex. So that's one thing to note about. And L here is going to be the loss function, and depending on what problem you're trying to solve, you can choose different loss functions. And we're going to have a regularization term. The regularization term again is a function of the parameters, and that's the basic setup. And I hope you've seen this setup before. And in supervised learning, even in deep supervised learning, this is the framework that we're going to be working with. So in this case, learning can be cast as an optimization. So for example, as I mentioned, for classification problems, we'd like to minimize classification error. But in many cases, loss function can often be viewed as a surrogate for what we want to optimize. For example, it could be an upper bound. For classification, typically, we use cross-entropy error loss. If you're doing regression, you can use L2 error loss and so forth. Okay, but that's the basic setup we're going to be working with. But let me give you an example of this setup in practice. This is ImageNet dataset. It has about 1.2 million images and 1,000 classes. And what you're seeing here is you're seeing examples of a hammer. And you can see the diversity of these examples. And it's actually pretty incredible that, you know, these models are able to classify all these different kinds of hammers very accurately. And let me just show you what the system would look like, and we'll go into details later in the tutorial. But just to be precise, input is a 225 by 225 image. It has 3 channels, RGB. Output is a softmax over 1,000 classes. And we're going to be optimizing this particular objective function that, and again, f here is going to be differentiable nonlinear function parameterized by parameters theta. In fact, the whole parameterization is going to be, in this case, the famous AlexNet model is going to have 8 layers. It's going to have about 60 million parameters, and it's a highly non-convex problem to optimize. The loss function is your regular cross-entropy error loss. And theta, for example, in this case could be L2, or it could be dropout and early stopping. And in this lecture, I'll go through different kinds of regularizers. So I think regularizers are very important for training these models. Okay, so this is the class of supervised learning, and it achieves, this particular model was developed back in 2012, achieved 18% top 5 error. Top 5 basically means that out of 5 classes, if you hit one of the classes is correct, you're counting it as a correct prediction. So this was viewed by many as a very important breakthrough back in 2012, was done by Alex Krzyzewski, Ilya Sutskever, and Jeff Hinton, where they've reduced the error rate substantially compared to a lot of standard techniques that people have used before. And just to show you what the system does, you know, if you look at this first image, the model correctly predicts that the class is mite, right? And then the second prediction is black widow or cockroach and such. Right, if you look at this image, it says container ship, pretty confident about container ship, but it also says it's a lifeboat and so forth. And the bottom row, you see some mistakes. I particularly like this one, where you see a dog with cherries, and the model says it's Dalmatian, right? But the correct class is cherry. So you can sort of see that in these kinds of data sets, there is also a lot of labeling, not really labeling noise, but there is, you know, these models, these images are noisy. Or this is an example of a squirrel monkey. So the model confuses Madagascar cat with squirrel monkey, right? So you can see that that's a wrong prediction. So these are class of models. In the terms of unsupervised learning, this is again something that we're going to be covering next tutorial. Given a set of, we're only given a set of unlabeled examples. So that area has been growing significantly in the machine learning and deep learning community. This is just one example. Given a set of unlabeled training examples without labels, can you actually build a model? And there are different kinds of models, probabilistic and non-probabilistic. Here's an example of something that's called the Boltzmann Machine model, where X here would represent a vector of word counts of a web page. H here would represent latent variables, so you can think of them as hidden topics. And if you visualize what these latent variables are doing, this is kind of the structure that the model is learning in an unsupervised way, right? So this is done primarily for dimensionality reduction, in this case, or visualization. But you sort of see that, you know, it nicely separates different classes, even though we didn't provide the model with the classes. And it's also sometimes, you know, if you look at that particular piece, it's kind of interesting. It's sort of, you know, sometimes you get a confusion between disasters and accidents, and they sort of lie next to European community monetary and economic policies, right? So that's something that the model is discovering, which is very funny. Here's another example of unsupervised learning, and this is done by a generative adversarial network. And again, I think you'll have a lecture on that. But just to show you, these are training examples, and these are samples generated by the model. And again, this is unsupervised learning because you're not really specifying the labels, but you can draw samples from these models. So it's almost like a generative model. And it's remarkable that the samples look really good in terms of, you know, what they're able to generate, which is pretty exciting and very remarkable. Here's another example of a generative model So here you have observed data. You have about 25,000 characters coming from 50 different alphabets around the world. So you have Arabic, Cyrillic, you have Sanskrit. And what you can do is you can simulate from this model. So here the model is generating images of Sanskrit, right? So you're saying, well, sample me images of Sanskrit. And the flickering that you see at the top, these are the states of the hidden variable. So you can think of them as states of the latent variable. Given different configuration of the latent variables gives rise to a particular Sanskrit character. So you can see that, again, sometimes these models are called generative models because you're actually trying to model the distribution over the input space. But let me start focusing on supervised learning. And I'd like to go through definition and training of neural networks, as well as look at the recent optimization and regularization techniques important for this class of models. And then tomorrow we're going to look at unsupervised learning, generative models, and research questions. I would also like to emphasize that some of the materials I borrowed from Hugo's class, Hugo Larochet's class, and I highly encourage you to go to this website, and Hugo has excellent lectures and class covering different kinds of models, convolutional networks, Boltzmann machines, and so forth. So I highly recommend that. So what I'd like to do is I'd like to go through the definition of neural networks, how to train them, give you some intuition about backpropagation algorithm, and also focus more on recent important techniques for training these models. Okay, so let me start with a very simple start here. I'm going to say, well, the neuron pre-activation or input activation is just given by a linear combination of your inputs. So this is your input. You just take a linear combination, you add the bias, and that's called neuron pre-activation. Neuron output activation, we're going to be passing it through some nonlinear function g, and that's called the activation function, right? So if g is logistic, or we're going to be using sigmoids. G could be sigmoid, sometimes people use 10H, and so forth. But you can see that this kind of looks a lot like logistic regression, right? In fact, that would be a logistic regression if you only had one hidden unit. W's here are going to be the weights, B is the bias, and G is the activation function. And we're going to look at some of those. So, and the activation function really, the G here determines the range of the output, and the bias only changes the position of the rift, right, where the bias is. So one of the most commonly used function is the sigmoid activation function. It squashes the neuron's output between 0 and 1. It's always positive, it's bounded, and it's strictly increasing, right? So that's one of the activation functions commonly used in practice. Perhaps in the last, 5 or so years, people switched to using rectified linear activation functions that I think was developed by Jeff Hinton back in 2011. This rectified linear unit, or ReLU, is bounded below by 0, so it just has this simple form. If it's below 0, it's 0. If it's above 0, then it's just a linear. And it tends to produce units with sparse activities, right? Because you're basically shutting them down. It's not upper bounded and strictly increasing. So in practice, people have to take some sort of care to make sure that it's not completely, so it's bounded above. So that generally can be done. But let me show you a single hidden layer neural network. It's basically, well, you have your hidden layer pre-activations, and you have a hidden layer activation function G, so it goes through all of these units. And then you have an output, and you typically have an output activation function. So for example, if you're trying to solve a classification problem, your output activation function would be softmax. If you're trying to solve regression problem, then your output activation function is going to be identity, right? You're just taking the outputs, and that would be your prediction, or that would be the output of a network, right? So different, depending on what you're trying to do, you can choose different output functions. And extension to the multi-layer neural network is very trivial, right? If you have multiple layers, you just repeat the same operation multiple times. You have layer pre-activation functions for internal layers. You have layer activation functions from 1 to L, and then you have an output activation function, right? So you can see that, these models, they have compositionality. It's a compositionally structured model, and you get to choose the number of layers or the number of hidden units within each layer, right? And if you think about it, you know, it kind of looks like a whole bunch of logistic regressions stuck on top of each other, right? But they're all working together to actually, you know, make a prediction. Capacity of the neural network. So this is just, I wanted to give you an intuition of what these models are doing. Every single so let's say every single hidden unit, it sort of carves these planes, right? But when you combine them, your decision boundary can be quite sophisticated. In fact, you know, even with a single layer neural network, you know, this is an example of a decision boundary produced by a network, right? So you can see that it can have highly nonlinear decision boundaries. So how do we train these models? Well, the first thing we need to do, as I mentioned in the beginning of the tutorial, is you need to specify the loss function and you need to specify the regularizer. So what do we actually need? We need to specify the loss function. Obviously, we need to specify the architecture of the neural network and its parameterization. We also need a procedure to compute the gradients of the loss function with respect to the parameters in order to do gradient descent. And we also need to specify regularizer, and we need to specify its gradients, right? So once we have the loss function, the gradients, and the regularizer and its gradients, then we can use gradient descent algorithms, right? And the basic form and the most successful form is stochastic gradient descent for training these models. So you can think of stochastic gradient descent as performing updates after seeing each example, right? So here for t equals 1 to capital T, the number of updates you want to do. For each training example, you compute the derivative of the loss function and the derivative of the gradient. Lambda here is the hyperparameter, which trades off loss function with a regularizer. And alpha here is the learning rate, so you update your parameters by doing gradient descent. And sometimes people talk about looking at the training epoch, and training epoch is just, you know, a single iteration of all examples in your data set. And so stochastic gradient descent, again, this is one of the dominant methods for training these models, particularly because of its scalability to training with very large data sets. And there are a whole bunch of very nice properties of stochastic gradient descent. It's actually, I'm going to show you later, it's actually very, very hard to beat stochastic gradient descent plus a few bells and whistles. And it's basically the state of the art. There's been a lot of work on trying to come up with the second-order optimization techniques. In some cases, the second-order optimization techniques, they do work. But in practice, still, it's very, very hard to beat stochastic gradient descent. So how do we compute the gradient of the loss function in these models? Well, it turns out that the backpropagation algorithm itself, if I go back here, the backpropagation algorithm itself is actually nothing more than a chain rule, right? You have this compositional structure, and when you compute the gradient of the loss function, you just backpropagate the gradient through these multiple layers of a neural network. So how does it work? In terms of computation, we perform a forward propagation, right, which can be viewed as an acyclic graph, which is actually how it's coded in a lot of software packages. So the forward propagation can be implemented in a modular way. For every single box, so let's look at example here, given x, you take a linear combination, given your parameters w, you pass it through nonlinear activation function to get the states of the hidden variables, and then you repeat this procedure again, right? So it's this very modular way of writing down the forward propagation. It's just a computational forward graph is an acyclic flow graph. And whenever you compute the gradients, using backpropagation method, you're essentially just making use of the chain rule. So you compute the gradient of the loss function with respect to each child box, meaning that you take this loss function, you compute its gradients with respect to f, and then you compute the gradients of f with respect to its pre-activation, and then with respect to the hidden variables and such. If you actually, you know, and you're calling backpropagation in reverse order. But at the end of the day, I would encourage you, for those of you who haven't looked at neural nets, just take a single layer neural networks and derive the gradient updates. It's a very useful exercise, and again, it's just a little bit of algebra and bookkeeping. But it's a fairly straightforward chain rule of calculus. In terms of regularizers, what do people use? Well, common ones to use is L2 regularization. Sometimes this is called weight decay in a neural net sort of community. Sometimes people use L1 regularization, right, which is just the sum of the absolute values. And the L1 regularization typically tends to make your model be sparse. So most of the parameters are close to 0. And both of these regularizers apply only to weights and not to biases. So these are the standard ones, but later on I'll tell you about a newer regularization techniques that you have to use to actually be successful in training these models. Now, let me switch a little bit and show you how the training is actually done. So what's the training protocol? So to train your model on a training set, and then for model selection, you typically use a validation set. So for example, this is where people are tuning the models in terms of hyperparameter search, right? So tuning the number of hidden layer sizes, learning rates, number of iterations. Initialization is also very important for training these models, so you can start off and you have to break symmetries. And then you estimate generalization performance using the test set, right? And what we'd like to do is we'd like to evaluate generalization of these models, which is the behavior of the models on unseen examples, really on the test set. And there's been also a lot of work on, how do we make more efficient and more intelligent search over hyperparameters, right? If you're an IT company with a lot of GPUs, grid search usually works pretty well. You just fire up 1,000 GPUs using different hyperparameters, and that works quite well. But there's been also a lot of interesting work on using Bayesian optimizations and tree-based optimization in order to do better hyperparameter search. This is actually one of the key areas for training these models, just because you have to tune the hyperparameters, and in many cases these models can be sensitive to the choice of the hyperparameters. Okay. To select a number of epochs, typically the commonly used technique is early stopping. This is where you're looking at the number of number of epochs, and you're looking at your training loss, and you're basically saying, well, if I start seeing overfitting on the validation, then it gives me the point where I need to stop. And early stopping actually works fairly well. This is a commonly used technique. The other thing I want to point out is that instead of doing stochastic gradient descent, where you keep updating every single example one time, you're actually going to be making updates based on a mini batch of examples, right? Instead of a single example. And you can view it a mini batch. Let's say a mini batch would typically contain 128 examples, or 100 examples, or 256 examples. And the gradient is the average regularized loss for that mini batch. And it typically gives you more accurate estimate of the gradient because you're averaging over a couple hundred examples. But more importantly, and the reason why people use mini batches is because you can leverage matrix-to-matrix operations, which are far more efficient whenever, for example, using GPUs or any other sort of accelerators. Because these GPUs are particularly made to be efficient for matrix-matrix operations. The other important point is it's also important to use momentum, right? And this is, you can think of it as an exponential average of previous gradients. So you take, this is the gradient of your loss for a current example, and then you basically have this term which has another hyperparameter beta, but it sort of looks at the exponential average of the previous gradients. And what it can do is it can get past plateaus more quickly by gaining momentum, right? So if at any subsequent time steps your gradients are pointing in slightly different directions, then effectively you have this averaging effect. And this momentum is actually very important. In fact, most of the state-of-the-art models, momentum is a must to use for training these models more efficiently. Now, let me just step back a little bit and highlight some of the differences, of what these models are doing. These models are sometimes viewed as learning distributed representations, right? So you have these multi-layer feedforward neural networks, but we'll also be looking in tomorrow's lecture at multi-layer graphical models, right? So models such as deep belief networks, deep Boltzmann machines, variational autoencoders. All of these models you can view as graphical models, undirected or directed, that have multi-layer representation. Each layer would learn something that's called distributed representation. What that means is that units in every single layer are not mutually exclusive. So each unit is a separate feature of the input, and two units can be active at the same time. And this is very different from, you know, some of the other techniques. For example, this is very different from partitioning or clustering the inputs, right? So, for example, in clustering, an input can belong to a single cluster, right? But whenever you learn distributed representation, every single input can activate multiple different features, or can, you know, if you think of it, it can belong to multiple different classes or multiple different clusters. So the activations are not mutually exclusive. And there is also a little bit of inspiration from Visual Cortex in terms of learning multi-layer representations, in terms of the human brain, also, you know, processing and also learning this sort of notion of high-level representations. So this is just an example that the first layer you might capture things like edges and primitive features. At the next layer you might start capturing, you know, more complex features like nose and eyes and mouth and such. And at the high level you'll start capturing the notion of a face and you know, the notion of the high-level object. This is just an inspiration. You know, we do see this kind of behavior when we're training these deep models, but at the same time, I don't think this is has been made very precise yet either, right? So this is sort of our just guesstimate of what the neural nets are learning. Now, let me, in the last part of tutorial, in the last half of the tutorial, I'd like to actually focus on more recent techniques. More recent techniques, there are two very important techniques that have been introduced in the last few years. One is the technique of dropout, which you can view as a way of regularizing the model. And the second one is batch normalization, which you can view as a sort of an optimization trick that allows us to train these models much, much better. So these two techniques are kind of part of any of the state-of-the-art model today. So let me step back a little bit and show you how, you know, what's the best practice for training these models. So given a data set D, you'd want to pick a model so that you can achieve zero training error on that model without using any regularization, right? So typically, let's say you want to train a model on your data set. The very first thing to do would be to pick a model and pick a size of the model and the architecture and the number of parameters so that you can actually fit the training, you know, set completely. And then you regularize the model, for example, using dropouts or using L1, L2 regularizers and such. So this is commonly how people build models, right? You fit the most complex model that can fit your training data, and then you regularize it. And that's the reason what's happening in practice when people look at, you know, data sets that have millions of examples. You fit the model that has, you know, 100 million examples. If you have billion examples, you find a model that has 2 billion parameters, right? So that's what's happening in practice. The more data you have, the bigger models you're training, right? Because these tend to give you better results and better performance. So it's kind of one of those things that, and that's why all the research in distributed computing, in being able to train these models more efficiently are now very, very important, particularly in industry settings. And the other point I want to point out is that stochastic gradient descent with momentum, batch normalization, and dropout usually works very well. And it's very hard to beat SGD with batch normalization and dropout. So if you look at a lot of recent papers, a lot of recent research, where people have tried to use second-order optimization methods and such, and some of the folks in my group are trying to do the same thing, it's actually surprising that it's so hard to beat SGD with momentum, batch normalization, and dropout. Right? So this is something to keep in mind. So let me get to the idea of dropout. So the key idea of a dropout is to cripple the neural network by removing hidden units stochastically. So it's almost like injecting noise or crippling the network for every single training example. Each hidden unit is set to 0 with probability 0.5. And what this does is this prevents the network from co-adapting to other units, right? So for example, it prevents the network to say, if this particular unit takes value 1, then the other unit should take value 1 as well, right? So it sort of prevents this notion of co-adaptation, and hidden units must be more generally useful. And the reason why is because at any point in time, any particular unit can be shut down, right? So it forces the model to kind of learn this redundancy and learn features that are more useful, because at any point in time, if you have a feature that's so useful for discriminating a particular class and no other features are useful, then this model will not find that particular solution, which is a bad solution generally, right? And then typically you can use a different dropout, but 0.5 usually works well. And one point I also want to make is that you're choosing which units to drop out for every single example. So even when you see the same example twice, the network that you're going to be using or the units that you're going to be dropping out are going to be different, right? So if you think about it, if you have in your network 1,000 units, there are 2 to the 1,000 possible networks, right, that you effectively fit in. How do you actually implement this in practice? Well, you can use a random binary mask, right? And what you're seeing here is you're seeing layer pre-activation, hidden layer activation, and output activation. So this is your standard neural network code where you compute pre-activation, you pass it through nonlinearity, you pass it through the output activation, and then you simply just do element-wise multiplication with your mask, with your binary mask. So that's a single change in the code. And the interesting thing is that when you're doing backpropagation, the backpropagation code remains the same, with the exception when you backpropagate, you just again do element-wise multiplication of this binary mask m. So it really just requires a single line change in the code to implement dropout. And I think that's why this technique has become popular, because it doesn't require any sophisticated update to the code or any sophisticated sort of training. It really is just a simple change in the code in the forward pass and in the backward pass. So what happens at the test time? At test time, you're replacing the masks by their expectations. And this is simply the constant of vector 0.5 with dropout probability is 0.5, right? So, and the other way to view what dropout is doing, you can view it as taking the geometric average of all neural networks with all possible binary masks, right? So you can think of it as saying, well, the way that I'm going to make my prediction, you probably use, you could use Monte Carlo. You can basically say keep sampling the masks and then average the predictions. And as the number of samples goes to infinity, this would effectively look at all of the networks and look at the geometric average of them. If you go beyond the single layer, typically if you have multiple layers, then the geometric average is not quite right, but it's just an approximation, right? So the way to think about this is that you have this exponential number of networks, and you're trying to train all of these exponential number of networks. They all share parameters. And at the end of the day, you're just taking geometric average of this exponential ensemble. That's sort of one justification. There's been a lot of work recently on looking at dropouts and trying to analyze it from Bayesian viewpoint and having a little bit more analysis of what exactly it's doing. And under certain conditions, people have shown what the dropout is doing. But in general, for when you have these multi-layer neural networks, it's an approximation. And so again, sometimes it can be viewed as a geometric average of exponential number of networks. And it typically beats regular backpropagation on many data sets. And this is now, again, part of the state-of-the-art model for a lot of different data sets. Let me jump now to batch normalization. That's another technique. So if you think about dropout, it's a regularizer. One thing I also want to point out is that the dropout probability of 0.5, you can use the dropout probability other than 0.5. But when we were publishing the paper, we thought about probability of 0.5 because reviewers wouldn't be asking us a lot of questions, right? Why would it be 0.5? Because if you had to pick a number between 0 and 1, you'd pick 0.5, right? So that's the reason why. But again, this is an adaptive parameter, and you can choose it using cross-validation, or you can tune it on a validation set. Now let me get to the optimization part. Back in 1998, LeCun et al. Showed that normalizing the inputs can speed up training, right? And the question that came up is, could normalization be useful at the level of hidden layers? So can we somehow normalize hidden layers as well, not just the inputs? And this was the technique of batch normalization. It's an attempt to do that by Ifo and Segeri at Google. And what they've done is they've done something very simple, but something also very powerful. So what you're doing is you're normalizing each unit pre-activation by subtracting the mean and standard deviation. So what that means, that basically means that the total input to every single hidden unit is going to be roughly 0 mean and variance 1, right? And that prevents the model to go into these funny regimes of saturation, right, where things become saturated which basically cripples the ability of training these models. During training, mean and standard deviation is computed for each mini batch. So you have a mini batch, you compute the mean and standard deviation, and the backpropagation takes into account the normalization, because the mean and standard deviation actually is a function of the mini batch. So you have to do backpropagation through the mean and standard deviation calculation. And at the test time, you just compute global mean and standard deviation. So you pass all your training data through the network, and you just compute the mean and the variance of every single hidden unit. And that's what you're going to be using at test time. Here's the pseudocode. You have a mini batch, the parameters. You also have 2 additional parameters, gamma and beta. You compute the mean for the mini batch, and this x here, remember, x it could represent hidden units in a particular layer, right? You compute the variance, and then you have this normalization. You have another hyperparameter epsilon just to prevent numerical issues. And you pass it through the batch normalizer. And now when you compute the gradients with respect to x bar, so you have to compute the gradients with respect to mean and the variance for these models. It's actually fairly easy to do, and the learned linear transformation can adapt to nonlinear activation functions, and you're introducing these additional parameters that kind of shift and scale the output as well. And this is, again, but the intuition here to think about what this is actually doing, this is essentially saying that the input to every single layer in a neural network is going to be 0 mean variance 1, right? Which is a very good regime to be in. So you never hit these saturation regimes. Well, why normalize pre-activations? Well, it can help keep the pre-activations in a non-saturating regime. That's important. And then you're going to be using global mean and standard deviation at test time, right? And as I mentioned before, this is just requires a final phase where, from the first layer to the last layer, you propagate all the training examples, you compute and store the global mean and standard deviation of each unit, and then you're using that for making predictions. And for the stopping, you can also use the running average. So this technique and this techniques, again, as I mentioned before, combining dropouts, batch normalization with momentum is kind of the state of the art right now in terms of optimization across a lot of different data sets and a lot of different application areas. So this is exactly what I've mentioned. In terms of optimization tricks, you still have to choose the learning rate, and there's been a few various recent algorithms. There's something that's called ADAM, ADAGRAD, RMS-prop, and such. But generally, you pick your learning rate by running examples on a subset of the data. You start with a large learning rate, you divide by 2 until the loss doesn't diverge, and so forth. So there are a few tricks that people are using to choose the learning rates, and then unfortunately it's still not automated. You still have to pick it by hand. Most of the time, the most sort of recent approaches are still using rectified linear units function as opposed to sigmoids or 10H nonlinearities. And I think the reason for that is because the optimization in the linear regime is easier, and it's also easier because you don't have to use nonlinearities. So computationally, it's much faster to implement rectified linear units. And you want to also, whenever you're initializing the parameters, you also want to make sure that you avoid units in saturation, or even though batch normalization actually helps you with that. And in terms of just whenever you're training these models, it's always useful to visualize features, right? So in this case, you'd want your features to be uncorrelated and have high variance. So what that means is that you want units to take values on and off or be active or inactive across different samples. And you want different hidden units not to repeat themselves, so not to be highly correlated. So this would be, visualization of a good training, right? You have different units activating for different examples. This would be an example of a bad training, right? Many hidden units ignore the inputs or exhibit strong correlation. So if you look at this particular hidden unit or this particular hidden unit, right, across all of the samples, this hidden unit is just basically 0. And this is very bad because it means that it's a useless, it's a useless feature. If it's 0 for all your training examples, it's useless. Or if it's active for all the training examples, it's useless as well. And so you can also see some units are highly correlated, which basically means that they're extracting the exact same thing. And that would be an example of, finding bad local optimum or not really doing something right when you're training these models. So have a look when you're training these models. It's also very useful to debug on small data set, right? As I mentioned before, typically you choose the model to overfit on a big data set, on your data set that you're working with, but typically it's a good practice to make sure that you can just overfit on a smaller data set. So if you pick 1,000 examples, make sure that your optimization, when you're training the model, you hit 0 training errors, all right? Because if you don't, that basically means something is wrong with your optimization, right? And if not, you have to investigate the following. So for example, you can see how some units saturated because of the first update. Sometimes if you initialize things inappropriately, you can get into this regime where most of the units are saturated. They're either 0 or they're saturated at some high value if you're using rectified linear units, and that's very hard to escape from that configuration. If that's the case, you have to scale down the initialization, you have to normalize your inputs. And then another thing to look at is the training error bouncing up and down. And if that's the case, you have to decrease your learning rate, right? Because that basically means that somehow your learning rate might be too high because the optimization doesn't really is not really working. Now, this doesn't really mean that you've computed the gradient correctly, right? You can still overfit with some of the gradients being wrong. And that actually happened to me multiple times when your gradient computation is not quite right, and it's very hard to test whether it's correct or not. Fortunately, there are now software packages like TensorFlow, PyTorch, ImageNet that actually compute the gradients correctly for you, but at the same time make sure that you check your gradients. And it's one of those things that you can overfit on a smaller data set, your training error can go down, but that doesn't mean that all your gradients are correct. And that's one of the things to watch out for. Okay? Now, in the last, in the last few minutes, let me just I'll show you some examples from the computer vision domain, because that domain has been very successful in the last 5 years. And this is an example of an object recognition. Given an input, identify which object it contains, right? And one of the most popular types of neural networks are convolutional neural networks. And I don't have time to go into specifics of convolutional networks, but you can think of convolutional networks as models that have very specific architecture. They use convolution as an operation instead of just taking the linear combination, and there are a few tricks to it for training these models, but they've been very successful for visual tasks. One of the most important questions is how do we select the right architecture? And a lot of people are joking that, before in the vision field and the speech recognition field, manual tuning of features was predominant, right? We were tuning features, people would figure out how to use different kinds of features. So for example, you can use SIFT, you can use hogs, you can use this and that. And now manual tuning of features is now replaced with manual tuning of architectures, right? So we've made a step forward to tuning features to now tuning different architectures. Depth, width, parameter count, many hyperparameters, number of layers, number of feature maps, learning rates and such. And grid search, you need a lot of GPUs. And I've mentioned before, you can use smarter strategies like random search, Bayesian optimization. So there's a lot of work on in that space trying to figure out how you can choose your hyperparameters more efficiently. But let me show you one example. Here's an example of an AlexNet. It has 8 layers. It achieved state-of-the-art back in 2012. If you remove this top fully connected layer 7, you save about 16 million parameters, and it only drops in error by about 1%, right? So maybe we can sacrifice that. But if you drop layers 3, 4, 6, and 7, right, you drop about 50 million parameters, then your drop in performance is about 33%. So the model really performs way worse if you are dropping some of the layers. So it seems that the depth is of the network is the key, and that's something that people have thought about. And it's the case that if you have 3 or 4 layers, people felt that was a lot. AlexNet came along, was 8 layers. And then Google, back in 2013, 2014, came up with the GoogleNet. It has 24 layers, and it's, the particular architecture that they've looked at. You don't really have any fully connected layers. Everything is convolutional. You have, 256 filters and so forth. So, and it achieved number of parameters was reduced to only 5 million. So we went from 60 million to 5 million parameters. So it's a drastic reduction in parameters, but the architecture has changed a lot, right? So now we have 24 layers, and it achieved 6.7 top 5 validation error on ImageNet, which basically was the state of the art, right? And the last part I want to point out is that last year there was a paper that introduced something that's called residual networks. And one observation that was coming from the residual network paper is that it's very, very hard to train deep networks, right? So for example, here's an example of training a 20-layer network versus 56-layer network. And it's not just that the validation error is somehow worse, it's actually training error is worse. So here's the training error. So it's much easier to train a 20-layer network than a 56-layer network. And that has to do with optimization, right? It has to do with the fact that when you're backpropagating gradients through 56 layers, there's problems of vanishing gradients and being able to do optimization correctly. And so key idea from the residual networks paper was to introduce these pass-through layers, or these skip connections. And skip connections have been around for a very long time. But they've done it in a way that was very clever, which is you have your input, and then you have an identity plus nonlinearity, and then the plus operator here. So effectively, your x, you can just copy the x through multiple layers, right? And so now you have these networks. I think they had a network with 152 layers. But having these skip connections so that information can actually jump between multiple layers. And when you compute the gradient actually, if you think about the way you compute the gradient will propagate through these nonlinearities, but it will also propagate just as an identity through these links as well. And that allowed these models to achieve state-of-the-art results on the ImageNet dataset. And I think that these kinds of results are very close to human-level performance on this task. Which was quite remarkable. So a lot of us are joking in the community that we went through, having 2, 3 layers to 8 layers to 22 layers to now 151 layers. Right? So it does seem to be the case that depth is very important, but optimization still remains a very hard problem for training these models. So let me stop here, and I think that we have about 6 minutes or so for questions. So maybe I can stop here and go to questions. Thank you.
Are there any questions for us? Ideally, come.
Sorry, can you speak up?
Can you hear me?
A little bit, but if you close to the microphone, that'd be great. Yep.
Can you hear now? Okay. So the question is, what do you think are the most interesting directions in deep learning? Is it about optimization or new architectures, something else? And another question about learning with few samples and deep learning.
Yeah, so these are excellent questions. I think that I will cover the open research questions in the next lecture tomorrow. So I'll show you what are some of the prominent research directions. From supervised learning, one of the important research directions that I'm seeing today is optimization. Right? So there's a lot of work on non-convex optimization because we don't really understand very well what's happening with optimization. And there's been a few papers that sort of contradict each other in terms of observations. People have tried looking at the second-order optimization methods, and in some cases it works, but at the same time there's something about interplay between generalization and optimization that have to be taken into account. So a lot of techniques that work in the convex optimization community doesn't really work in whenever you're training these nonlinear models. So I think that that's an important research direction. Tuning different architectures. This is something also very interesting, but it's very hard to figure out what are the right architectures. So if you look, for example, at residual networks, the idea of having skip connections have been around, but the idea of making them fairly precise is the way they've done it by introducing these identity functions specifically to help optimization was very neat, and that gave them significant improvements. But from my perspective, I think this interplay between optimization and generalization is a very important research direction that we don't really understand very carefully what's going on. In fact, let me just point out, if we look at the residual network, if we actually look at the residual network results, the way that the models were trained, they were trained using stochastic gradient descent, and the way it was trained is, you're training with stochastic gradient descent, and after a certain time, you basically divide your learning rate by 2, and you keep training, and then at a certain point in time, you divide it by 2. So a lot of it looks more like, I train my model, I go drink some coffee, I come back, I divide my learning rate by 2, I go drink more coffee, you look at what's going on, you divide your learning rate by 2, and so forth. And this is something that gives you state-of-the-art results, and it's very hard to beat. So obviously, we're doing something wrong. So it has to be better optimizers and better optimization techniques. But at the same time, if you look at batch normalization, right, it gave rise to, a far better optimizers. But there is no clear understanding as to what batch normalization is doing. There's been a few papers showing that it has a connection to approximating diagonals of the Fisher information matrix, right, and also connections to Newton method, or diagonal of the Newton method. But there hasn't really been any precise, justification for these models. Same thing happens for dropouts. So I think there is a lot of interesting work that can be done in that space, particularly if you're interested in supervised learning. But again, tomorrow I'll show you some of the research directions within the deep learning community in general, not just in supervised learning, but also in unsupervised as well. And then to your point about one-shot learning, yes, it's a very important problem, and I'll mention it in tomorrow's lecture as well. A lot of these models, a lot of successful models so far, make use of large number of labeled examples, and that's a to some extent it's a problem. That's not how humans learn, but at the same time, the most success we've seen are the settings where you have lots and lots of labeled examples, right? And to some point, you can train these models to be even better than humans. Like, I can build a model for classifying between different kinds of mushrooms, which is an example of ImageNet, and I can do it way better than humans can, provided that I see lots and lots of labeled examples of different kinds of mushrooms. Because these models are very, very good at detecting patterns and detecting very specific low-level patterns that even for humans would be difficult to detect.
Are there any other questions? Yeah.
Can you hear me now?
Yeah. Yes.
Good. Hi. I was wondering, so you said that one of the reasons you said batch normalization worked was because it pushed the data into the linear part of the activation function, right? And so it's not saturated too much. My question is, for me, I always thought that this saturation part was an important part actually of the nonlinear part of the function is actually some very important part of the network. So it seems that it's a bit contradictory to what you say. And maybe your hypothesis could be tested. I mean, if what you say is true, then there should be a difference between when you use a batch normalization on a network with value activations and when you use it on something where you have a hyperbolic tangent or some sigmoid or so, where I mean, where sort of, is it something that you have noticed?
No, this is something that I haven't tested myself. I think that what's happening is that, particularly for ReLU activation functions, right, what batch normalization does is, you're right, it ensures that you sort of sit in this linear regime. For ReLUs, it's a little bit different, right, because for ReLUs, if it's less than 0, you shut down the features. But even for 10H or for sigmoids, batch normalization helps. Because if you think about it, right, you're just saying that the mean should be 0 and variance should be 1. Typically, you can have sort of a bimodal distribution, which basically says some of the units are close to 1, some of the units are close to -1, which, you know, and then you have these scaling factors that I've mentioned, gamma and beta, so they can expand things a little bit and shrink it, right? So if the network really wants for certain things to really be saturated, it can make sure that they are saturated. Right, but at the same time, the saturation. One of the problems with the saturation is that if you saturate by too much, like if the probability of the hidden, let's say you take a sigmoid, if 0.9999999, so you're sitting very far to the right, it's very hard to come back from this, right? So what happens during optimization and why batch normalization helps is that it ensures that your network sits in a linear regime at least during the first part of training, as you start training the model. But then you have these adaptive parameters, gamma and beta, right? So if the network really says, I want my, I can always set my, let me just maybe quickly go to this point, and I can, yeah, so over here, you have these parameters, gamma and beta. So these parameters are there for a reason. Because if I set my beta to be the mean, and I set my gamma to be the variance, I can recover my unit exactly. Right? So in terms of the capacity of the model, I'm not somehow crippling it. Because if I initialize, if the model says I want my beta and gamma to take those values, then I can undo what batch normalization is doing. Right? But you can test these hypotheses. I agree with you. You can test these hypotheses on ReLUs and 10H and such. What typically happens is that initially gamma is 1, beta is 0, which basically means you live in a linear regime. As the network progresses, as the training progresses, if you want some of the units to saturate and kind of go into the nonlinear regime, then you can set, then the model can adapt gamma and beta, right? It can still make beta be 0, but that it can get gamma to be 2, for example, which will force some of the units to be, you know, not just around 0, but be pushed away from 0, right? But you can see from mathematical perspective, you can also recover what batch normalization is doing, or you can undo batch normalization, basically.
Yes, okay, thanks. That answers. But however, has it been tested actually, this difference between, or observed this difference between ReLU and other activation functions?
I don't know. I suppose that people have probably studied most heavily for ReLU activation functions, but not as heavily for 10H or sigmoids. I think that I've played myself a little bit with batch normalization with 10H units, and I do see speed of convergence for 10H units. With batch normalization is much faster. But at the same time, you know, it doesn't mean that somehow, you know, if you don't do proper sort of normalization, or if you do sort of proper learning with small learning rates, you can achieve the same. You might be able to achieve the same, you know, generalization error. So I don't think it has been tested properly as to what's happening. What are the key differences between 10H, sigmoids, and ReLUs whenever you apply batch normalization? Maybe that's a study that would be very interesting to see.
Okay, thanks.
Okay, I think we have one more question on the other side.
Hello, can you hear me?
Yes.
Hi. Yeah. So with other needs optimization and regularization trick that you introduced in the lecture, right? Is there still any need to use a random restart to avoid local minima anymore in practice?
So typically, you know, so there's a long time ago, I guess, you know, 5-6 years ago, there was a hypothesis that it's a very highly non-convex space, right? So in order to find a better local optimum, you have to do multiple restarts. And then it's this idea that somehow you have a lot of bad local optimum and maybe some kind of good global optimum that we don't know about. In practice, what happens is that with these tricks, with batch normalization, with dropouts, because you're introducing stochasticity, typically you don't really kind of hit very different local optima. So it's not like if you start with one particular configuration and you do, 1,000 restarts, one of them will find a way better solution than the other ones, right? So it seems like most of the local optimum that these models are finding are all equivalent. Well, maybe not equivalent, but they're all kind of live in the same regime, right? They give you pretty much similar generalization performance. So people generally don't do multiple restarts to find better optimal point. What people do is instead they do multiple restarts with different hyperparameters, because that affects your performance, in much sort of bigger ways, right? So it's typically you do many restarts from the same point, but you do it with different hyperparameters. Obviously, you can do multiple restarts from the same hyperparameters, and people typically do that to just assess variability of your network and variability to the randomness that you're injecting at the training time, and also reproducibility. Just if I run it multiple times, can I reproduce my results? That's roughly, but it's not typically being done for finding a better local optimum.
So we have one last question. Yeah, Andres.
Hi, can you hear me?
Yes.
So my question is, seen in one of these neural networks, it's good at domain transfer. So if I can train a network on ImageNet and I image and still so that is that domain application. But at the same time, we have things like adversarial example. So it seems to be super non-robust with respect to a vocal. So how does that, on the one hand, super robust with respect to range? So do you have like?
Yeah, it's a good example. So your example, let me just repeat what you're asking me because you were breaking up. You're basically saying that these models are robust because you can train it on ImageNet, for example, on one data set. You apply it to another data set and it works fairly well. But at the same time, with adversarial examples, I can tweak my input a little bit and my model can give completely sort of random predictions.
Right, that's a question. And in particular, since if you use convolution, then you do Max Planck, you actually introduce invariances with respect to local effects. So
right.
We would expect it to behave the other way around.
Yeah, that's right. So let me get to the question of transfer learning. Yes, that is correct. This is actually the surprising thing that surprised a lot of people in the community because there was a paper recently that was claiming that they take ImageNet features. These models was trained on like hammers and mushrooms and different kinds of dogs and all kinds of stuff. And you take these features and they were using it for like classifying or fine-tuning it to like classifying medical images, like cancer cells and such. And they've shown that it actually works reasonably well, right? Which is remarkable. Like it's completely bizarre. And it's actually working fairly well. Like, for example, one of the interesting things about ImageNet is that it's specifically designed not to detect people or recognize people because there are so many images contain people that they basically said that if we start, include a person class, then 50% of images will conclude a person. 50% of all the data set would include a person. So they specifically deliberately took this class out. But if you take ImageNet features and you use them in caption generation system that I've shown you at the beginning of the tutorial, that was used based on ImageNet features, it has no problem learning about people having a dinner or two people standing next to each other and so forth, a crowd of people walking around. So it shows about generalizability of those features across a whole different domain. So somehow it's learning these robust features. It's kind of like saying, well, a person is like maybe what it's doing is basically picking up features that basically says, well, a person is really like, you know, like a dog mixed together with mushrooms and a hammer, right? If you think about it, like you have these high-level features, it just finds the right combination of features. So it's very robust, and I think that really to test the performance of these models, see how well they do, I think that's a really good idea to see how well they do on a lot of other different tasks and look at the transfer learning. And that's why people have really started looking at these models precisely because of this generalizability. Now, with respect to adversarial examples, it is true that I can take the input and I can perturb my input in such a way that my model will be completely confused about the class, right? And that is problematic. But there is one thing to note about these models. Adversarial settings is a little bit unfair to the extent of the following. The assumptions that these models are basically making is that the data and the classes come from some distribution, right? There is some true distribution that generates the data, generates the classes, and you fit in your model. And that's a standard statistical learning theory approach, right? And if your test data comes from the same distribution, I can make some statements about how well I will generalize. What happens with adversarial examples is very different. With adversarial examples, what I do is I change the input itself. And if you look at the way that they change the input, they take the gradient of the loss function with respect to the input. What it does is it basically changes the input in such a way that it's no longer represents a valid image. So if you look at some of these examples, right, it kind of like creates these high frequency, it introduces sort of these high frequency parts of the image that we as humans can't really see, but the network basically, you know, it's something completely different, right? It's no longer a real image, right? And that's why if it's no longer a real image, you step off the image manifold. And if you step off the image manifold, you can't have any guarantees, right? I can always, like, what I can do is I can take my blue channel and increase, you know, some of the pixels by 100, right? Visually, it's not going to change, but it will completely mess up the network because some of my units will get saturated and so forth, so it will just disbalance my entire network. And the other thing is that the network in these adversarial settings have to produce 1 of 1,000 classes, right? So it has no choice to say, I don't know. It has to produce, it has to give you one class. And if you disbalance the network, then, you know, your output is going to be basically random. So you can always make that. And that's why I think that there's a class of models, generative models, that somehow perhaps could sort of learn about the distribution of the input so that they can detect these adversarial attacks and basically say, look, something is funny happening to the input distribution. Or from a novelty detection standpoint, to say this is not part of the real image. I think that there's been a few papers that basically try to say, well, I can fool the network by moving along the image manifold, so I can, you know, convert a cat into the dog, into a funny-looking dog, but it still remains on the image manifold, so it still contains all the statistical properties of an image, and then you're confusing the network. Then that's you know, that's a very good example to have, and that basically means that the model needs more examples, perhaps, to even, you know, to train better. But that's the reason why it's robust to images, but it's unrobust to perturbation of images, especially if this perturbation doesn't really, or jumps off the image manifold, right?
All right, thank you.
Hello? Are there any questions from the other room, actually? I'm just looking at the other room. Stenya holding a mic.
No, we don't have any questions here.
Okay, great. Okay, so thank you very much, Russ. It's really great to have you here by video. Yeah, and I guess we'll see you again tomorrow, your morning,
Yeah.
our afternoon.
Yep.
Yeah,
Thank you very much. Yeah, so tomorrow we're going to look at unsupervised learning and open research questions. Thank you.